Okay, we're back again. We got a couple more videos to look at for doing some derivative example problems. Some of these are a little more challenging. This one has a quotient of two functions, but they're not both polynomials. We have an exponential in the numerator and a polynomial in the denominator. So f of x equals 4 to the power 3x minus 5 in the numerator, and the denominator is 2x squared plus 5. We want you to find the first derivative, the second derivative, and the equation of the tangent line at x equals 1 for this function, and graph all those things along with the original function together and see what you see in terms of the graphs. So let's start by getting the first derivative. If you haven't done this already, please do so now. Press pause. Well, I think hopefully you saw that the first thing we want to do is to do a quotient, or the last thing we would do in evaluating this is to do the quotient, do the division. So the first thing we'll do is a quotient rule here. I went ahead and made the substitution u equals 3x minus 5 to save me some writing, because I know I'm going to need to do that later on at some point, at least in my head, if not on paper. By the way, when you're doing derivative problems, as you do pretty much anything in mathematics, if you skip a step, you miss the problem. You absolutely cannot skip any steps in mathematics. However, what you can do sometimes is apply some shortcuts, or you can apply some of the steps and do them in your head. So as you get better and better at this sort of thing, you might be able to do more and more of these steps in your head, but you cannot skip them. So you actually have to do the substitution regardless of whether you do it in your head or on paper. I'm going to be explicit about it, do it on paper. So with that substitution, we got the derivative of 4 to the u over 2x squared plus 5 when we apply the quotient rule. So it says the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. The derivative of the bottom here is just 4x, and the derivative of the 4 to the u is ln of 4 times 4 to the u times the derivative of the u being the 3x minus 5, so that derivative is just 3. Alright, calculus is done with that part of it. With finding the derivative, we just got to do a little algebra. Notice they both have a 4 to the u, so I factor that out front. What's left? When we divide this by 4 to the u, we have a 3 times ln of 4 times the 2x squared plus 5. And here we just have the minus 4x. And I'm going to distribute this and show you that this is just a polynomial in the top with the 4 to the u. So we got 4 to the u, 4 to the 3x minus 5, and what's in parentheses is just a quadratic polynomial. It's 3 times ln of 4 times 2 is 6 ln of 4, that's the coefficient, times the x squared. And then we have 3 ln of 4 times 5 is 15 ln of 4. That's our constant term out here. And the minus 4x is our linear term. So we've got an x squared, an x, and a constant term in there. Now you could leave it like this. We could write this as using the properties of logarithms. For example, write this as ln of whatever 4 to the 15th is there. Or we could write this 4 is 2 squared, so it would be and then rewrite it as maybe 30 ln of 2. We wrote that way. We'd probably write this as 12 ln of 2 times x squared. So there are some alternate forms that we could leave this in, but there is the derivative. Let's check it. As we check any of our derivative problems, we put the original function in here for y1, being sure to put parentheses around the numerator and the denominator. y2 is the numerical derivative of y1 with respect to x. Evaluated x, y3 is the final answer for the derivative. Turn off y1 and look at y2 and y3 in the table, and they do match, and that is corroboration that we did this correctly. Okay, now we're going to take another derivative. Okay, again, the last step is a quotient, so we're going to use the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. Now, this is a little harder because we've got to use a substitution and a chain rule for this last derivative. And this first one here, we've got to use the product rule. Okay, so let's look at the product rule. So we still got this factor out front. We still got this 2x squared plus 5 squared again, so that makes the power of 4 there. Simplify that a bit. Alright, now let's look at this derivative right here. Okay, that's a product, so we use the product rule. First times derivative of the second plus the second times derivative of the first minus, and then over here we have this is our original part here is recopied, and then we take the derivative here Okay, I'm going to do the substitution in my head. Let's pick a letter, say v. This is v squared, so we get 2v times the derivative of v. The derivative of 2x squared is 4x. So I did a substitution in my head that time. Alright, let's see what we've got here. We still got some derivatives that we still have to take. Alright, so notice I recopied all this stuff just like it was here. Recopied it on there like it was here. Recopied this part here. And where I'm working is inside this parentheses starting right here before the 4 to the power 3x minus 5, and after this 4 to the power 3x minus 5 here for this. Now let's see which one do we want to do first. Okay, let's do this part. This is just a quadratic, so this is not too hard. It's 2 times the coefficient, so that makes it 12 ln of 4. Power goes down to 1. Derivative of the linear term here is just the coefficient -4. The derivative of this part is 0 because no x's in that. That's a constant. So derivative of that's 0. Alright, that took that derivative. This is derivative of 4 to the u, so that's 4 to the u times the derivative of the u, which is 3. Alright, I think the calculus is done. Now, we got a big mess there. See if we can clean this up a bit. Notice that, let's see, right there's a 4 to the 3x minus 5. And both this one and this one have a 4 to the 3x minus 5. Factor that out. Also have the 2x squared plus 5 to the first power here and here, so I can bring that out front. Okay, so if I factor just those two things out, let's see what's left. Let's look here. That cancels that down to the first power, so that's right here. And I've divided this out of both of these, so that's gone here. That leaves the 12 ln of 4x minus 4, which is right here, plus, well, we still got the 3, we still got the ln of 4, and we got all this stuff here. Okay, and here, let's see what's gone. We have this is gone because we factored it out, that exponential, and this polynomial here. But we still got this 2 times 4x is 8x times 1 is negative 8x here times this. Okay, let's distribute that on the last part here. Negative 8x times 6 is negative 48. Then we got this ln of 4 that x times x squared is x cubed. Negative 4 times negative 8 is positive 32. X times x is x squared. And then we got 8 times this negative is negative 120 ln of 4 times x for that last term. Over here we're going to do some distributing too. I'm going to leave this right like it is for the moment. And then this is going to distribute, let's see, where am I? Leave that out there. And I've got these, let's see, we still got that term, the 12 ln of 4, we got the minus 4. Now we're going to take this 3 ln of 4 and distribute it. So this is 18 ln of 4 squared times x squared minus 12 ln of 4 times the x, and this is plus 45 ln of 4 squared. Let's get a little bit nasty on the arithmetic or the algebra here. Now notice this 2x squared plus 5 at the front that I factored out cancels this one down to the first power. That's pretty typical what happens when you have rational functions. Well, this is not quite a rational function, but the quotient rule oftentimes happens. If this already has a power in the bottom, the ultimate result, this will be one less power in the bottom once the cancellation occurs. Even though we're doubling the power here, part of that will cancel out. Alright, so let's see. I think the next step, let's see, what did I do here? I just combined some like terms here. So let's see, here's the x squared term, put it first. Then we got x terms here and here. 12 ln of 4x minus 12 ln of 4x. Hey, look at that, that cancels out. So that was convenient. And then this part right here, 45 ln of 4 squared minus 4 together is the constant term. And I just got that written like it is. And now combine like terms here. Here's an x, well actually I distributed this out. I did the 2x squared times this. Gives me an x cubed term. An x to the fourth term, excuse me. And that's 36 ln of 4 squared. And then I've got this we get a bunch of x squared terms. The 2x squared times this is negative 8x squared. This is plus 90 ln of 4 squared x squared. And then we get the 5 times the 18 ln of 4 squared. So if you put all that together, combine that together, you get this right here as the coefficient of the x squared term. And then you got the 5 times these two guys here is a constant term. That's right here and right here. See, 5 times 45 is 225. 5 times negative 4 is negative 20. And we still got all of this down here. Now combine like terms, put it in decreasing order. Here's our x to the 4th term. Our x cubed term is over here. X squared term here and here. Put that together. The negative 8 and the 32 combine to give 24. And then we have an x term here. And the rest of this stuff is constants. This part right here is our constant term. So here's our coefficient of our x to the 4th. There's our coefficient of x cubed, x squared, x, and constant. And then we still got our exponential in the numerator, and we still got this same denominator we had before, but this time it's to the 3rd power in the end. Alright, kind of messy for the second derivative. Several of these problems, the second derivatives are a little messy. I designed all these problems to give us some interesting challenges for the first derivative, and as a result, sometimes the second derivative's got to be a little bit challenging. But notice that, regardless of that, we can actually use the derivative rules we've come up with, and basically pretty much any kind of function that's built up out of elementary functions, we know how to do a derivative of it. Now, it might be messy, like this one, or even messier still if we make a more complicated function, but given enough time and patience, we can figure this out. Here's the check. Since I had this y3 as the original first derivative, I changed y2 to be the numerical derivative of y3 with respect to x, evaluated x, turned off y3, put my second derivative in y4, watch your parentheses there, kind of messy, and then check the tables for y2 and y4 and make sure that they match, and they did. So we check that. Now, let's see what we've got here. If you look at the original function, the numerator is always positive. So this thing never crosses the x-axis. And if you look at the denominator, it's always positive as well, so it's never undefined. So actually, this is actually a continuous function made up out of quotient of two continuous functions. It's never 0 in the numerator or denominator. So it never crosses the x-axis. In fact, it's always above the x-axis. So the graph of the original function is, wait a minute, is that true? Yeah, the original function should be above the x-axis. Yes, that is true. Okay, so it's above the x-axis, and all three of them look like they're basically indistinguishable from the x-axis here on the far left, because that is a horizontal asymptote. So as x goes to negative infinity, the top of this thing goes to 0, and the bottom goes to infinity. So the whole thing's going to 0 for sure. Similarly here and down here. That exponential term is the one that really dominates and takes it there quickly. Okay, so it's a lot like an exponential function in its basic shape. Looks like it's increasing concave up the entire way. Let's continue to look at this and verify that. Let's look at the first derivative. Well, again, the denominator is always positive. The 4 to the power, whatever, is always positive. And you'd look at this function right here and see if it was ever 0. Now that's a quadratic. You need to use the quadratic formula on that. But it looks like from the graph that it actually is never actually 0, which would mean that the original function is increasing the whole way, and that seems to be what we have here. We could verify that by looking at the quadratic formula on this and showing that it doesn't have any real solutions. The second derivative, okay, we got a big mess here, but it's a 4th degree polynomial here. The denominator is always positive. the exponential part's always positive. It turns out that this part's always positive too, although it's not obvious at all by looking at it for that fourth degree polynomial. But if we see all three of those functions are increasing concave up, kind of like an exponential function. Now let's look at the tangent line. Take the original function, plug in 1. Okay, and that's here's worked out right here. 1 squared is 1 times 2 is 2 plus 5 is 5. 3 times 1 is 3 minus 5 is negative 2. 4 to the negative 2 is 1/8. Oh, 1/16. 1/16 times 1/7 is 1 over 112. So 1/112 is f of 1. So 1 comma 1 over 112 is where it is right here, just barely above the x-axis. And that's where the tangent line is going to touch the graph of the original function. Go to this first derivative and plug in 1 here, 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 and here, and we get this right here. Okay, so let's work through this. 3 times 1 is 3 minus 5 is negative 2, so this is 4 to the negative 2, which is 1/16. In the denominator, we got 1 squared is 1 times 2 is 2 plus 5 is 7. 7 squares, we got 7 squares 49 times 4 square. 16 times 49 is 784 in the denominator. In the numerator, let's see, what else do we have here? We get a 1 here, so this is 6 natural log of 4. That's 4, negative 4. 15 natural log of 4, that's 21 natural log of 4 minus 4. Or again, I could write it as 42 natural log of 2 minus 4 over 784. But anyway, that's the y value. That's the y value on the derivative at x equals 1, which is the slope of the original graph, or the slope of the tangent line. So that becomes our coefficient right here. Then we have our x minus 1, and then we have our y value of the original one. So there's the equation of the tangent line. When we graph that, that's the purple graph here. And we see that it does touch right there, and at least close by right in here, it does look very much like the graph of the original function. Of course, not so much when we get way out here or way out here. Okay, got a couple more of these for you to try. A couple more examples. Some of these are challenging. Okay, see if you can work out this one. Whoops. I want to give away the answer here. Okay, so f of x is the logarithm base 5 of the absolute value of 5x minus 7. See if you can figure out how to work that problem. Find a derivative, first derivative, second derivative, and the tangent line when x equals 1. And see if you can work that out before you watch the next video.